So here's my question that we want to do. Another fill in the blank one, 2NO2 gas, N2O4 at 100 degrees. So, oops. Says this is the following data that's completed, and they want you to go ahead and determine the K from it, okay? So your ice table is given. And it's NO2 and N2O4. Zero 0.0200, and that's a 0, okay? And then all they tell you is you have 0.0172 here in equilibrium. So from this information, you have to fill in the blanks. So basically in this question, if it was in a word problem, it would say, in the beginning, before the reaction, NO2 was added, and this is the amount, 0.02 molarity of NO2 was added. At equilibrium, NO2 was found to be 0.0172. What is the K for this reaction? That's what they would ask. So they'll just say, I put in this, and I've got something at equilibrium. The things that they don't mention, just fill in with a 0. Okay, if they don't put it in, they're not going to mention it, so you just put a 0 in. So now you have to find out the difference between here and here. So can you tell that it went down from here? How much did it go down by? If you just take the difference here, and you actually see it's going down by negative 0.00, while it's going down 0.0028. Okay, and then you have to figure out what this change is going to be. So how are you going to do that? Well, what was the change here in terms of X though? It looks like it's going down. So at NO2, the coefficient is 2. So that means negative 0.0028 is actually negative 2X. Okay, so if that's the case, each X should be 0.0014. Agree? Let me zoom in so you guys can see a little better. So once you know that, let's go over here. If this is going down, reactants are going down, products must be going up. And what is the coefficient for this guy over here? This coefficient here is 1. So it should be, in this case, it should be positive X. Okay, so that means in here it's plus 0.0014. So my answer here, 0.0014. Okay, now to get the K, you simply take your formula. What was the formula? N2O4 to the power 1 over NO2 squared. So 0.0014 over 0.0172, and this is squared right here. So you should get an answer of 4.7. All right. So basically, that's one form of problem that we're going to get. And we're going to move on to the next portion here. Let's see. Well, not everybody is here yet, but whatever. We are going to do a quick poll right now. Because it's not that cold, but if you were somewhere really, really cold today, we're actually pretty warm in comparison to the rest of the country. So hot chocolate, hot coffee. I guess I should have said it was, assuming it's hot coffee. I guess iced coffee is coffee too. You're still freezing. Maybe for lunch, you guys need to have hot soup today. Yeah, Texas. It's actually the whole middle of the country. They're all like negative. And we're over here in our 60s and 70s. Hot tea and hot chocolate. Yeah, it seems like hot tea and, well, hot tea is not as popular, but a lot of people like hot chocolate. All right. So some of us, let's see, it's kind of, yeah, it's everywhere except Florida. That's funny. Well, it's kind of nice here today. If you missed a class, do we email you the poll question when we rewatch a lecture? Yes. That way I know you are participating, and that's why the polls are random during different random times. So you kind of have to watch the videos to be able to tell. All right. We got a couple of us that haven't voted, but we're gonna go ahead and end polling so we can continue with our lecture. We'll share results. Obviously, everybody likes hot chocolate. All right, we'll stop the share here. And let's continue with our class here. So far we've been talking about K a lot. K means the concentrations at equilibrium. What if you wanted to describe concentrations that's not at equilibrium? Like say, can you describe the concentrations at I, during I, like initially? You know, like, or maybe if you reach equilibrium and someone did something to it and made changes to it, now it's no longer K. So K is only during equilibrium. If the equilibrium is not established or equilibrium is disturbed, you need another way to describe the concentrations here. Okay, so what we want to know is how to do that. So on slide 35, we talk about reaction quotient Q. So Q looks exactly like K. The only difference is Q concentrations are at non-equilibrium scenarios. Okay, so at non-equilibrium scenarios, so basically maybe during your initial step, you have your Q. Or maybe after you reach an equilibrium, someone else changed the concentrations again, then you have another set of Q. But no matter what, it's not K because it's not at equilibrium. So whatever is not at K, the concentrations are going to be at Q. Okay, formula is exactly the same thing. The only thing is these concentrations here are not at equilibrium. Okay, so the thing is, any system that's not at equilibrium is going to work itself towards the equilibrium. So we can say anytime you have Q, it's going to try to turn itself into K because K is equilibrium and it's stable. So anything that's not at equilibrium will try to change its concentrations over here till the Q looks like K. All right, so I wanted to show you the difference here between Q and K. So we knew that Q is at non-equilibrium, right? So, space here. All right, so let's say I have a reaction. So like earlier, we were trying to imagine numbers. Like, you know, the big number means it favors products for K. A small number means it favors reactants for K. So in this case here, I'm just going to pick something that's really, really simple. But let's say my K is 1. Okay, if K is 1, I guess, you know, it doesn't really favor one way or another because it's like almost even. But so in this case here, for an example, just simplify, making the case really, really simple. If K is 1, it could be maybe 10 over 10. Agree? Like just like a number, like 100 over 100, 10 over 10, 1 over 1, that all gives you 1. All right? So let's imagine we're trying to get K as 1, and you have a Q that's smaller than K in this case. So maybe my Q in this scenario was Q is 0.1. So how did they get 0.1? Maybe they had 1 over 10. Okay, so and remember we have the reaction of A going to B. This is my reactant side, and B is my product side. Okay, so in this case here, you have very little B and a whole lot of A. You agree? So in this case, when Q is smaller than K, okay, when Q is smaller than K, because you know everyone's trying to get the K, it's kind of like sometimes in class I like to say this is like peer pressure, chemistry peer pressure. All the Q's want to be just like K. So they'll change themselves, conform themselves till they can get K, okay? So if Q is smaller than K, we have too much of something. Too much what? So if you wanted Q to turn into K, you wanted the ratio to be the same. But now you have way too much stuff on the bottom, agree? Because it's not 1-to-1 ratio, now it's 1/10 ratio. So basically you have too much reactant here. So basically, when Q is smaller than K, it's a smaller number because you have too much reactants on the bottom. So if you have too much reactants, reaction is going to try to fix that. So a reaction will proceed to reduce reactants. Now, when it reduces reactants, it also increases products. So I write N increase products because it's reversible, right? So if you reduce the reactant and increase product, it means it's going like this direction. Use some of this to make, use some of A to make some of B to try to equalize things. So since it's going towards the right side, I can say reaction shifts right. So this is in the forward direction, or reaction moves towards the product side. We can say towards products. Okay, so that's one scenario where if Q is smaller than K. So when Q is smaller than K, reaction will shift right because it's trying to make the reactant go down and product go up until it gets to that ratio that it wants. Okay, now what if you had the opposite? So in this case, Q is bigger than 1, so maybe Q is 10. So in this case, maybe your ratio was 10/1. Now you'll see you have, this is product side, right? Products. And this is reactants. So if you were trying to get K as 1, you really have too much products now, okay? So Q is bigger than K, we have too much products. So what the reaction will do is kind of try to reduce the products and increase the reactants by shifting to the left, okay? So I'll say reaction will proceed to reduce products and increase reactants. Reaction shifts so instead of going to the right, now it's going to the left side towards the reactant. So shifts left, or we call it the reverse direction towards reactants. Okay, so basically the concentrations will change until the Q finally gets the ratio that makes it turn into a K. And once it reaches K, it's at equilibrium, it's happy, it doesn't change anymore. Okay, so now sometimes, you know, like we say here, sometimes we have zeros in there. So let's say we have a 0 somewhere in our, when Q equals to 0. So how can you get a 0 when you have a 0 on the top or something on the bottom? Like say maybe we'll put a number 1. Okay, so in this case here, you have no products. And you have some reactants. And it has to shift to turn to 1 because it's the ratio they were trying to turn to a number, right? So in this case here, when Q is equals to 0, you have absolutely no products. So what the reaction needs to do is generate some products. Okay, so when it generates products, it's gonna use up some reactants to make some products. Maybe they'll go to like half and half, you know? So I'll write it out. When Q equals to 0, you are missing products completely. So a reaction will proceed to make products. So when it makes products, it's going to shift right, okay? Shifts right or in a forward direction. What if our 0 is on the bottom where you have absolutely no reactants instead? Okay, if Q was, I guess we say 1/0, we got no reactants. So in this case, I guess we call it infinity. So this one here, no reactants. And we have some products. So in this case here, when Q is infinity, you are missing reactants. Okay, so the reaction needs to make reactants. So reaction will proceed to make reactants. And that means it shifts left or the reverse direction. Okay, so these are some scenarios where I'm just putting in numbers so you can see the ratios, but really you're just looking at how does a Q compare to the K? Is it bigger or smaller than K, or is it 0 products or 0 reactants? And which way will my reaction need to go? It's useful. This is a really useful building block for our a lot of the chapters behind this. So you want to make sure you know this part. Okay, so we just got to understand how the Q will change in a certain direction, make the reaction go a certain direction, depending on what the K and Q comparisons are. So it's actually given to you on slide number 36, where it tells you what happens. And of course, the one thing I didn't write down is when Q is K, it's at equilibrium. It's happy, it won't change. Okay, so there's these scenarios here. We wrote it all down, how it will shift. If Q is exactly the same as K, it's happy, it won't change. So now let's go ahead and try a problem, okay, that requires you to compare Q to K and see which way it's going to shift. So now, always remember the question doesn't tell you, oh, by the way, you need to compare Q to K here. They're not going to tell you that. But what it says is here, they'll give you a reaction equation. So let's say this is my reaction, I2 and Cl2 goes to 2ICl, and it says which direction. So it's very important for you to be able to predict which direction the reaction will go, okay? Will it proceed to if Kp is 81.9. So remember, Kp means it's in ATM units, okay? And Pi2 is 0.114 ATM. And PiCl is 0.355 ATM. And P of Cl2 is 0.102 ATM. So they gave you a scenario here, and they're not going to tell you what to do. So in this kind of situation, if they ask you which direction will it proceed, and give you some sort of concentration or pressure, you want to go ahead and say these values will give me Q, and I'm going to compare it to this K and see which way it's going to move. Okay, so the first thing you want to do is put in what Q is. So the formula for Q in this case would be ICL squared. I wrote molarity, but really it's pressure, but it's just ICL squared, and then you want to do I2 on the bottom and CL2 on the bottom. Okay, so let's go ahead and put that together. So it's 0.355 ATM, and this is squared up here. So Q and K don't have units here. Okay, so you don't need the units. ICL 0.355 squared, and then I2 is 0.114, and then CL2 is 0.102 on the bottom. Okay, so in that case, put this in your calculator. This should be still pretty simple. Square the top, divide by these two numbers on the bottom. If you're doing it straight, remember to put a parentheses outside of these two in your calculator. You get 10.8. Okay, and then you're like, okay, well, I have 10.8 and the K is 81. So clearly my Q is smaller than my K. That means I have too much of what? If the number is small, that means I have too much stuff on the bottom. We have too much stuff on the bottom, which the bottom stuff is reactants. So which way is it going to shift? It's going to shift, too much of this stuff is going to shift to the right towards the product to reduce the reactants and increase the product. So it will say it will shift right towards products. Okay, so that's one example here. Let's try a few more. So this one here is just a combination of different scenarios. So the equation here will be given. CH4 plus 2H2S, and then CS2 plus 4H2, and this is gas. And then the K here is given as 3.59 at 900 Celsius. So they're going to say at the same temperature here, we did the reactions, and they want you to find the Q. So these are all not at equilibrium concentrations, okay? So they'll give you a set of 3 reactions. So right now, set 1, set 2, set 3, and you have your set of concentration, CH4 concentration, they put in something, H2S, they put in, and then CS2 and H2. We put in everybody that's not solid or liquid. So all of them goes in, okay? So in the first reaction, they have 1.15, because this is in molarity, and then 1.2 of H2S, 1.51, and 1.08. So they want you to find which way will it shift with the first reaction. So Q is, in this case, what? It would be H2 to the power 4. I guess I should write it up here. Q formula is H2 to the power 4 times CS2 divided by CH4, and then H2S squared. Okay, so in this case, the Q would be, let's see, 1.08 to the power 4 times 1.51 divided by 1.15 and 1.2 squared. Then you get a number here. So in this case here, my number is 1.24. We'll leave some space between the second and third reaction. So if Q is 1.24 and K is 3.59, again, Q is smaller than K, right? So when Q is smaller than K, that means you have too much stuff on the bottom. The reaction will shift to the right. Okay, so the next scenario, we'll have another set. where it's 1.07 for CH4, 1.20, 0.90, 1.78, okay? So try doing a Q for me here and see what you guys get. And then I want you to do another set here with 1.10, 1.49, 1.10, and 1.68. Try getting the Q there for these two. Give you a few minutes to do that. So what did you guys get for the Q for the second one? You do basically 0.9 to the power 4 times, no, actually it's 1.78 to the power 4 times 0.9 divided by 1.07 and 1.2 squared. Okay. Yeah, 5.86. So if it's 5.86, what does that look like? Q is now bigger than K. So now you have the opposite problem. Earlier it was smaller, right? Now it's bigger. So if it's bigger, that means you have too much of your products on the product side, the top stuff. Too much of the H2 and CS2. So reaction is going to have to shift towards the left side. To reduce this and make more of that, it's going to go to the left. Okay, now try doing the third scenario and see what you guys get for your Q. So a lot of times in these questions here, they're not going to say, oh, find what the Q is. Sometimes they'll say, because the Q is this and the K is that. But a lot of times they don't tell you, they just ask you which direction will it proceed, and you just need to know. Yes, the next one is 3.59. So what does that mean? This one is exactly the same as that now. So yes, the same. So it's no change because it's already at equilibrium. All right, perfect. So just kind of keep this in mind, okay? So we kind of need to know, and we know which way things are going to change. Now, with this skill here, okay, combined with the skill from before, I'm going to show you a new type of problem. So in the beginning, the first kind of problem we did, okay, I'm going to flashback, was basically I have some sort of initial concentrations and I have some equilibrium concentration. They give you usually just one. From one, you back calculate the rest. Agreed? But they have to give you one equilibrium. And then when you back calculate all the stuff, you can calculate the K. All right? So now this type of question now is a little bit different. So I'm going to write it up and we'll see how the question differs from the first type. A lot of students get them confused. They don't know, like when you see the question, they don't know what to do with it. So I'm just trying to point it out so maybe you can distinguish that. And this comes with a lot of practice. You're going to have to practice quite a bit to be able to get this. So here's the first difference. The question earlier was saying, here's my initial and here's my equilibrium, find the K. But this one here, they gave you the K, okay? So they gave you the K and it says a reaction mixture at 2000 degrees initially contains N2 is 0.200 molarity. So they gave us an initial. That's good, okay? And it says another initial, O2 is 0.200. Find equilibrium concentrations. Of the reactants and products at the same temperature. The reason why they say the same temperature is because the big K equilibrium constant actually changes with temperature. So when you change the temperature, the K changes, so they have to state the same temperature. And really, do you need the temperature in your calculations? No, not at all. They just put it there to distract you, just another extra term. Okay, so the difference here is, earlier's question, they would give you some initial and one of the equilibrium. And then from there, they ask you to find a K. This question here, here's my K, here's my initial, find the equilibrium. So it's kind of like just a backwards reverse question, right? It just looks reverse. So the same, we kind of set it up the same way, but the way to solve it is a little bit different because we don't know which direction things are moving, right? You have to predict which way it's moving because they didn't give us a hint on one of the equilibriums. They say, go find all the equilibrium. So if you don't have one of the equilibrium concentrations, you really don't know which way things will shift. And that's why I taught you how to compare Q to K so you can see which side it will proceed towards to. So that's your first step, okay? But anyway, they gave us the K here. The K is 0.1. What's the formula for your K though? The formula is, I like to write the formula out, is NO squared over N2 to the power 1 and O2 to the power 1. And that number equals to 0.1 at this temperature of 2000 degrees Celsius. Okay, now I can start my ice table. So my ice table will have all the gas stuff in here since they're all, everybody's in there, so they're all gas. So sometimes students don't really understand how to fill an ice table. You get to this point by practicing. And you put in just the chemical. You don't care about the coefficient. The coefficient tells you how much change, but you just put in all the, when you put the reactants and products and just literally put one of each in there. N2, O2, and O, okay? What's my initial? Well, they told me initially you put in 0.2 of N2 and 0.2 of O2. They didn't mention NO, so that one's 0. Okay, so that part is still the same. Now, the next part is, in the earlier question, you'd have one of these guys down here, and then you can back calculate the change. But now we don't have any of these guys here. But I did teach you how to predict this direction of changes if you took Q and compared it to K. Okay, so if this is the K formula, my Q formula is exactly the same using these numbers, agree? So what's my Q here? NO is 0, there's absolutely no products, right? They didn't put in any products. So the Q is actually a 0 because Q is 0, it's gonna shift towards the side that has the 0. So I like to help you guys remember is anytime there's a 0 in there, it will shift towards the side that's a 0. Because earlier we said if you have no reactants, no products, it will shift towards the product side. Let's say one of these guys were a 0, then it would be shifting to that side. It doesn't matter if both of them are 0 or one of them is 0, as long as one side is 0 because you're multiplying the numbers together. So that means it will shift towards the side that has a 0. Okay, so if I know NO is 0, it's going to shift towards the side that has a 0. That means this side is positive because all the products are going up and my reactants are going down. Agree? So that's the comparison of Q to K. We took Q, compared it to K. We just said, well, in this case, our Q is 0. All right, so I guess I'll write down the Q. Q is 0 squared over 0.2, 0.2, and it's 0. Q is 0. So because Q is 0, we know it's going to shift towards the product side, and I put the change here as positive, this side is negative. Okay? So how many x's will it change by? This is one coefficient, so it's 1x, agreed? This is another one coefficient, it's going to go down by 1x. How much is this going to go up by? It's going to be 2x because of the coefficient here. So now it looks kind of the same like what we did before, except we don't know the value of x. That's the only difference. You don't really know what the value of x is. If you had one of these numbers, you could have guessed, you could have back calculated what x is, and all these would become numbers, but we don't. Okay? So what I'm going to do is we have to solve for x now. Now, the one way we can solve for x is we know k. We know k equals to 0.1, so I'm going to go ahead and put equilibrium terms. This is 0.2 minus x, 0.2 minus x, and this is 2x. I'm going to go ahead and plug these x terms into this k formula and try to solve for x, okay? So basically k equals to 2x squared over 0.2 minus x, 0.2 minus x, and that equals to 0.1. Okay, so now we want to mathematically solve for x, and once we get what x is, then we can find out the equilibrium concentrations, basically. So let's go ahead and do this. So when you see something like this, this repeats itself, so this is really 2x squared on the top, and on the bottom is 0.2 minus x, and that's squared, agree? And that equals to 0.1. So if I took a square root on both sides, like square root of both sides, I can get 2x over 0.2 minus x equals to the square root of 0.1. Okay, now then we want to go ahead and still solve for x. So I'm going to multiply both sides with 0.2 minus x. So this one becomes 2x here, and it's 0.2 minus x times square root of 0.1. Okay, and then I'm going to go ahead and multiply them out. So you can put the square root of 0.1 in the calculator and get the number, but since I know it's a long number, I'd rather just write this number and then do my calculator later. Okay, but you do whatever you want as long as I try not to round till the end, but you can round anytime because the sig figs here are only, well, the k is only like 2 decimal places anyway. So let's go ahead and continue with this. So 0.2 times square root of 0.1. So I'll write that term. So the first term is 0.2 times square root of 0.1. And then you want to minus square root of 0.1 x. Okay, and that equals to 2x. So what I'm going to do is put all the x's on one side. So do your square root of 0.1 here. It's like square root of 0.1. It's like 0.31622 blah blah blah, but we can just round it for now. Keep it at like 0.32. Okay, so this is 0.32, this is 0.32 right here, okay? So I'm going to go ahead and say, well, this is 2x, and then this is 0. It's 3/16 right here. See that? So 2 times that is, you actually round it to 0.063. And then this is 0.32x. So that's what this turns into, okay? And then I'm going to put my x's together. So I'm going to add both sides with 0.32x. So 2.32x equals to 0.063, okay? And then x is 0.063 divided by 2.32. And you get your answer as 0.027. So this is in molarity here. All these guys here in molarity, so this is what x is, 0.027. So once you solve for what the x is, you can then go back over here and say, well, I can get my equilibrium concentrations now. So nitrogen gas at equilibrium is 0.2 minus x, which x is 0.027. Is this 0.200? Remember from the question. Anyway, so you get the answer for that. That one is 0.173. And then molarity. And then O2 is exactly the same answer. So it's also 0.173. And then NO at equilibrium is 2 times X, so 2 times 0.027. And that would give me 0.054. So that's how you would find the equilibrium concentrations of these guys here. Now, if you were to plug these in here, the answer should be pretty close to 0.1 also. If you plug these guys in the formula, you should get 0.1 as your K. Okay? Why is it minus square root? Because of this minus right here. You know how you like multiply, I don't know how you guys like expand it. So this is a negative x here. So I just stuck the number. You know how you have a number and an x? That's why it's negative, because there's a negative x here. Okay, so everyone good with this? So this question is basically a combination of all the skills that we learned before combined into one problem. Okay, how to like determine which side it's going to go and what the x's are. In this case, actually solve for the x using algebra. All right, so let's try another problem. After this, I promise I will show you how to simplify the math out. So I just want to show you, like, this one here is going to be a little longer, because in this case here, we had it a little easy. We could just square root everything. The next one, you can't square root, so you end up using the quadratic formula. Okay, but I'm going to show you just one example in the quadratic formula one. I try not to put the quadratic stuff on your test because it takes forever to do. I try to give you problems where you can simplify a little bit. On your homework, though, expect to see a lot of the quadratic stuff, okay? On your homework, I believe they don't let you do the shortcut at all, but towards, like, you know, the next chapters, we'll be using a shortcut a lot, okay? So for this chapter, try not to use the shortcut too much, and I'll teach you when you can use the shortcut anyway. There's only certain scenarios where you can use it, and it will apply the next 2 chapters a lot. So let's continue with another question here. Now we have another equation. So you have N2O4 gas. Okay, it's going to turn to 2NO2 gas. And your K is given, Kc is given as 0.36, and it says it's at 100 degrees Celsius. Remember, the 100 degrees is just really a distraction, because you have to get the calculations for also 100. So sometimes they don't even mention the temperature. Assume it's the same temperature, okay? So initially NO2 is 0.100 molarity. Find equilibrium concentrations at 100 Celsius. So basically the same temperature there. All right, so the K did not change, this K stands. So the first thing you always want to do is to write the formula for K, okay? So I like to write a formula for K. So first thing is you need to identify what kind of problem it is, okay? They gave me a K, they gave me initial, and they asked for equilibrium. This is a sign where I need to do the solving for X one, okay? In the earlier question we first did in lab and in the lecture before this, we always did where they gave you initial, they give you one equilibrium, and you back calculate, and they don't give you the K. They ask you to find the K then. Okay, so that's kind of the opposite way. So now we have this kind of problem. They gave you the K, write on the K formula and say that equals to 0.36. So my K formula here is NO2 squared divided by N2O4. And that equals to 0.36. Okay, so when that equals to 0.36, let's go ahead and set up our ICE table, okay? So on your ICE table, it says initially NO2 is 0.1, so that means this one's NO2, that's 0.1, you have some product, you have absolutely no reactants. So N2O4 and NO2 is in your ICE table. You have 0.1 of this guy, and you have absolutely nothing of that. Okay, when absolutely nothing of one side, remember what this one here, we go towards the side that has a 0. Now, if there wasn't a side that was 0 like earlier, like this question here, everybody has some number, there's no 0, then you actually have to calculate the number and see which way it's going to shift. But if there's the 0 in your problem, you really don't have to calculate because you need to just focus. There we go. So if there's a 0, we know it's going to go towards the side that has a 0. Okay, if it's going to go towards the side that has a 0 because we're comparing Q to K, Q in this case is infinity because it's something over 0. So we are going to make sure the reactants go up and the products go down. Okay, now go up by how much for N2O4? It will just be 1x and it will go down by 2x. Okay, and then you just say if 0 plus x is x, 0.1 minus 2x, I'll just have to write it out, 0.1 minus 2x here. And I'm going to take this and plug it up here. Okay, so K equals to 0.1 minus 2x, and you got to square that divided by x. And that equals to 0.36. And now you just want to solve for x basically. So in this case here, we will be using quadratic formula. You're not gonna have to use the quadratic on your test, so I don't have the quadratic formula on there for you, so don't worry about it. But if you see it during your mastering quizzes or homework, make sure you have it handy. I'll write it out here, and remember those mastering assignments are all open book, so just make sure you have your notes in front of you. Okay, so I'll write it out. We'll work it out. I guess I'll write the quadratic on the side here. X is minus b plus minus b squared minus 4ac over 2a. And then you have to remember what ABC stands for. I'll go through that with you. So let's go ahead and work on this. So I'm going to go ahead and multiply both sides with x. So I get 0.1 minus 2x, and this is still square, and that equals to 0.36x. Okay, then I'm going to, whatever you do in here to open it up, I think you guys call it, you call it FOIL? I think you call it FOIL. But I just learned it with a formula. It's like, so basically a squared and b squared and 2ab. But whatever you guys did, okay? So foiling. So you do this foiling here. So I'm gonna get your answer out. So a squared, I don't need the zeros. I'm gonna keep the zeros off, so less numbers to write. 0.01 minus 2ab, so 0.04. It's not 0.04, it's just 0.4. To AB and b squared. So it's 4x squared. Okay, when you FOIL it, that's what you should get on this side. And then I'm going to just copy down my 0.36x on this side. So now what I'm going to do is go ahead and move the 0.36x over. So I have to subtract both sides by 0.36x. So let me write it out. So 0.01 minus 0.4x plus 4x squared minus 0.36x equals to 0. Okay. Now I'm going to clump the x together and the 4. So I'm just going to rearrange it. Okay. So see how this 4x squared is right here? So I'm going to write 4x squared is right here. And then I have 0.4x and 0.36x. They're both negative. I'm going to put them together. So negative 0.76x. All right, you guys see that? And then I have this one here is positive 0.01. So that equals to 0. All I did was just rewrite it a little bit, okay? So in this case here, that's how you're going to get your A, B, and C. Basically, A is the number stuck to x squared, B is the number stuck to x, and C is the number without an x. So my A here is 4, my B here is negative 0.76, my C here is positive 0.01. Okay, and then you use your ABC and you plug it in this formula right here. So because it's quadratic, there's going to be 2 answers. Only one of the answers will make sense. Okay, basically, you know how you can't ever get, can you ever weigh out negative 2 grams of a chemical? Can I tell you to go weigh out? Hey, everybody, now go to the balance and go weigh out for me negative 2 grams of something. Or when you're trying to bake, you use your scale. Does it ever show you a negative number? You can't weigh out something negative, okay? If you can't weigh out negative grams, you cannot have negative moles or negative molarity, which is why like in our lab calculations, if I told you you had negative molarity, you did something wrong. Negative moles, something is wrong. You probably made a math mistake. So whenever we solve for the x here, the answer that gives you a negative molarity is the wrong answer. We don't want to use that, and the other one will work. So there's going to be 2 options here, okay? So let's go ahead and try to solve it out, okay? So my x here equals to minus b. So minus b is just positive here. So positive 0.76. And then you got to have 2 options, plus and minus. That's why we get 2 answers here. And then put the b squared and 4ac in there. So b squared is 0.76 squared. So I'll put negative 0.76 and I'm going to square that. Minus 4, A is another 4, C is 0.01, okay? That term is square root on the bottom. And then over 2A, which is 4. So then we simplify this a little bit. So this is now 0.76 plus minus. Let's get the answer for in here. So you take 0.76 squared and then minus the term for AC here. And then square root it. You should get around 0.646, blah, blah, blah. So I'm just going to go write 0.65 down for you. And then divided by 8. That's okay. Sometimes the Zoom is a little crazy. I'm glad I don't get kicked out. If I get kicked out, all of you get kicked out too. That would not be as entertaining, huh? You'd be like, what happened? Like earlier today, my computer was acting crazy. The camera wouldn't work. Anyway, so now we have 2 options, okay? So you take 0.76 plus 0.65 divided by 8, or you can take 0.76 minus 0.65 divided by 8. So you have 2 options of x answers. The first answer for x is 0.176, and then the second answer for x is 0.014. So now you have to decide, well, which one is going to give me only a positive answer but not a negative molarity? So let's take a look at my equilibrium here. So x doesn't help because both of them are positive. So that's not going to help me pick which one. But on this one here, it says 0.1 minus 2x. Well, this is bigger than 0.1. So if you take 0.1 minus 2x with this number, this x here, it's going to give you a negative number. Agree? So this one here, we will cancel out. So I'll write this down here. Can't use this guy. Can't be used because it produces a negative molarity. So what we're going to do is keep this guy as my x. Okay, so this is my x. This is in terms of molarity here. So I'm going to go ahead and plug it up into this equilibrium step. So let me go ahead and write on the side. So N2O4 at equilibrium is x. It's just x. It says over here, just the x, okay? So it's 0.014. Now if I want to NO2 at equilibrium, it's 0.1 minus 2x, so 2x is 0.014. Put that in, so answer in molarity. That would give me 0.072 molarity. So you'll get your answers that way, okay? So like I said, this one takes a long time. Oh, great, camera's acting up again. I don't know why I keep doing that today. So anyway, so we have this here. This is how we're going to be solving a problem like this. Basically, your answer, the key is to write the K formula, fill out the ICE table with terms of x, and then solve for x. So there's a few ways to solve for x, right? Sometimes you have to use quadratic, which is really, really long. I don't like it, so I try not to put it on your test ever. But on your quizzes, it's pretty randomized. Sometimes you might get it on the homework I'm mastering. I have that one, you might run into it. Okay, so now sometimes you take the square on both sides to solve for your x. Now I want to show you another way to simplify your math here, so maybe you don't have to use your quadratic ever. Okay, there's only a few scenarios where you get to use your simplification. In chapter 16, you're still not really trained to do the simplification yet, but I'm just going to go ahead and show you guys anyway. So it will be very, very useful from the next chapter onwards. And so there's a few things we have to look out for, okay? So to simplify our math, we have to go over some things. The rule is K must be super small. So you're like, okay, super small, that's subjective, that's so relative. So what's super small? Because like over here, our K was what? 0.1 and 0.36. It's not that small, but they're like, okay, well, what do you call small? How small should it be? So I'm gonna put a second thing down here next to it. It says initial concentration is a lot bigger than K. Okay, that gives you a little bit more idea of how small K must be. So it says initial concentration should be a lot bigger than K. Then you look and you're like, well, my initial concentration is pretty much just about the same as my K. So in this case, you can't do the simplification. Again, here, 0.36 and 0.1 is really similar. So you can't use the simplification, okay? So that's why I wrote it down here. You don't use it for every single scenario, but a lot of times in the next couple chapters, we will be able to use this, okay? So how much bigger is considered big enough? So a lot of people ask me, they're like, I can't tell. Okay, so if you can't tell, a general idea is 10,000 times. So I'm gonna go ahead and write it out, okay? If the initial concentration is about 10,000 times, so 10,000, or we can say times 10 to the power 4. (10,000) times bigger than K. I think that's pretty obvious. Now we know, okay, so the concentration is going to be big compared to the K. So my K must be really small. Maybe my concentration is 1 molarity and my K has to be about 1 times 10 to the power of minus 4 because it's 10,000 times difference. Okay, so our concentrations tend to stay in regular numbers like 1.1, and then so you just basically look for a really, really small K, about 10 to the minus 4-ish. Okay, so here's an example how we can simplify our math. So why we can apply it when these two conditions fit. I'll write it out. So here's an example where you have A turning into B. And it says here K is 1 times 10 to the minus 12. Oh, you're like, okay, that looks small. That's good. That's really small, right? And it says initially A is 0.1. So I'm really using a very, very simple example. So it's going to look exceptionally simple. And then after that, we'll do like a problem that will kind of be more typical. Okay. All right. So let's do this. Find equilibrium concentrations. All right. So we see that, yes, my A is 0.1. And my K is so small, it's way, way, way smaller than 10,000 times smaller, right? It's like 10 to the power 11 times smaller. Okay, so I'm like, okay, that means I can simplify my math. So how in the world am I going to simplify my math? So it all comes down to, we want to set up the same question. So we say, okay, if I know what the K is, let's go ahead and write the K formula. The formula for K is B over A. And that equals to 1 times 10 to the minus 12. Okay, you go through the same motion, write the K formula, write what the K equals to, and then fill out your ice table. So you have A and you have B, and we want to set our ice table. And it says, initially I have A as 0.1, so this one goes here. Well, they didn't even put the 0.10, so I guess we can add a 0 here. All right, and then B is 0. Because they didn't put any of that. And then say find equilibrium concentration. So your job now is, again, to do the same thing. You have to decide which side is it going to shift towards to. So I like the ones with zeros in it because it shifts towards the side with 0. Remember, if it doesn't have a 0, what do? You have to actually physically calculate a Q and compare it to the K then. But because there's a 0, we kind of have a shortcut. It goes towards the side that has a 0. So this one's positive, this one's negative. Agree? Now, this is 1x because I just made a very simple example of 1x over there. So this is 0.1 minus x, and this is simply x. And I'm going to go ahead and plug this over here. So this is where you can start to see where our simplification can be. Okay, so b is x, a is 0.1 minus x. So here's the scenario. If my k is really, really, really small, all right, what does that mean? It favors which side at equilibrium? It favors the reactant side. Agree? The K is so small. At equilibrium, you'll have a ton of A left over. A ton of it. That means if you start off at 0.1, a ton of the A stays behind and only a very, very small part of it turns to B. To be your x. So x is really, really, really small compared to 0.1 now. Agree? Because we say because the K is so small, A is highly favored in a ratio. So in the end, this x is very, very small compared to 0.1. How small? Maybe it's like 0.0000001 or something like that. So 0.1 minus 0.000000009, what's the answer? When you round it up, it's still 0.1 because it's so small. So what I'm going to say is because x is so small, okay, we're going to pretend it's not there. So let me write it out. So we're going to cross this x out compared to 0.1 because it is so small compared to 0.1. So it's only compared to a number. You can't cross this x out because we know it's a small number, but any small number compared to 0 is still a number. So we'll just have to keep the x here. But if it's something like plus x or a number minus x, a number plus x, well, you can assume this x here is really small. It's not going to make a difference after you do a significant rounding. Okay, so if that's not significant because it's so small, that means in my math here, I can cross this guy out and call this insignificant right there. So that's how you simplify your math. You start crossing out some x's. So I have students that they get really x crossing happy. They end up crossing every single x they have in the equation. And they're like, hold on a second, I just crossed all the x's out. What am I solving for? So you can't cross all of them out. There's only certain things that you can cross out. So do not cross out x that were related to 0. It's just x is small compared to a number. If it has a number in front of it, like something minus x, something plus x, then yes, you can say the x is insignificant compared to that number. Okay, so now since that one, the x is gone here, and that still equals to 1 times 10 to the minus 12. So then you'll literally get your answer. X is now 1 times 10 to the minus 12 times 0.1. So x is 1 times 10 to the minus 13 molarity. So as you can see, x is really, really small. 0.1 is 1 times 10 to the minus 1, and the minus 1 times 10 to the minus 13, the answer is so small. Okay, so to check this, so every time you take a shortcut where you cross x out, you want to make sure you check to make sure you're good. So I'm going to give you an idea where you're about 5% would consider it small enough. Okay, so what you want to do is to check it, you take your x, okay, after you solve it, after the simplification, you divide it by your initial concentration. And you want to make sure it is less than 5%. So if it's less than 5%, we just say, well, it's small enough, we'll cancel it off, okay? Times 100. And this answer must be less than 5. Because we're talking percentage here, okay? So in this case here, let's try 1 times 10 to the minus 13 over 0.1 times 100 to get the percentage is 1 times 10 to the minus 10%. So yeah, it's really small, it's less than 5, so it's okay for us to approximate the math or simplify it. All right, so that's just how we would do a very simple example. So I want to go ahead and write out a problem that we can work together on this, okay? So let me go ahead and turn over. Hopefully you guys are done writing that. My question here is 2H2S gas goes to 2H2 gas plus S2 gas. And then they say Kc is 1.67 times 10 to the minus 7. You're like, yeah, it's small, I like that. If it's big, I don't like it because I have to do the long math. But this looks small, but we're not all there yet. It says if a 0.500 liter reaction vessel initially contains 0.0125 moles of H2S at 800 degrees Celsius, find equilibrium concentrations. So they're a little tricky here. They didn't even give you the molarity. They give you moles and liters. So you actually have to calculate your molarity first too. Should we check the X before we cross it out? No, we usually cross it out if it fits the conditions. K is really small and 10,000 times smaller than your initial concentration, and then we check the X. You can't really check the X before you cross it out because you can't solve for the X. You have to get the answer for X once you solve it to check it, okay? So let me go back to the question here. See how you get the X here? So once you cross it out, then you solve for your x and then you check it. Because if you don't, if you don't have your x to compare, if you don't cross it out yet, and you can't solve for your x because the math's longer. This one obviously you can still do, but sometimes the math is really, really, really complicated. So cross it out first and then check it later. Okay. But if you follow the idea where it's about 10,000 times difference, I promise you it will work. So what we want to do here is go ahead and set it up. So it says here, what's my molarity though? Moles per liter. So 0.0125 divided by 0.5 gives me 0.0250. So yeah, that is about 0.25 times 10 to the, 2.5 times 10 to the minus 2 compared to 10 to the minus 7. That's 100 times, 100,000 times difference. So we're definitely good with our math simplification there. Okay, so that's how I'm checking, like just taking your initial molarity and making sure it's about 10,000 times bigger than the K. So in this case here, what I want to do is go ahead and set up my K formula. So Kc is H2 squared times S2 divided by H2S squared. And that equals to 1.67 times 10 to the minus 7. Okay, you have that right there, 1.67 10 to the minus 7. And then we're going to go ahead and set up my ice table. Remember, H2S goes in there because it's a gas. You only drop solids and liquids, but all of them are gas here. So H2 goes here, and S2 goes here, and then you have your ice table. So initially, what was our molarity of H2S? It was 0.0125 moles divided by 0.5 liters. And that gives me, so I'll write it on the side here, H2S initial is 0.0125 moles divided by 0.5 liters. So 0.0250 molarity. So I'm just going to write 0.0250 right here. And didn't mention the other guys, so there are zeros. So that's great, because when there's zeros, I like to go towards the side that has the 0. Remember, the Q shifts towards the side that has the 0, or if Q is smaller than K, to the right, Q is bigger than K, and it goes the other direction. So in this case here, 0.0250, this would be plus, and that's minus. Okay, so with the plus and minus put in, and then you decide how many x's there are. So because the coefficient is 2 for H2S, this will be minus 2x. This one is 2 for H2, it will be plus 2x. This one is just 1 S2, so it will be just plus x. All right, so then you want to write out your answers in terms of x and then solve for x. So 0.0250 minus 2x, and then you have 2x and x. So we can't cross out this x or this x because it's like compared to 0. But this 2x here is small compared to 0.0250 because we said this number is a lot bigger than your k. We know it's mostly not going to shift. This 2x here is going to be a really, really small number. When you try to subtract 2x out after sig-fig rounding, you really just get 0.0250 again. So we want to assume this guy is insignificant. Okay, we'll cross this one out. We'll call this too small to be significant. So we can cross that one out. So that means when you go to your K formula, you have 2x on the top here, that's squared, x on the top here, and then to the power of 0.0250, and then you had that little 2x here, right? But we're going to cross this little guy off and then square that. So can you imagine if you had to square the 2x and then you had x up here? So the math would have been pretty crazy. So that's why we just go ahead and cross this one out and say, well, it's safe to assume 0.0250 minus 2x. 2x is so small, it's going to be less than a small number. And then we're going to go ahead and assume it's insignificant. And that, this whole term here still equals to 1.67 times 10 to the minus 7. And now we do our math here. So 2x squared is 4x squared times x will be 4x cubed. and divided by 0.0250 squared, that would be 6.25 times 10 to the minus 4. And that equals to 1.67 times 10 to the minus 7. So 4x cubed in this case is this term times that term. So I'll just write it out. 1.67 times 10 to the minus 7 times 6.25 times 10 to the minus 4. And then if I want to get my x cubed, I divide this side by 4. So x cubed equals to that term again. Divided by 4. And then to get just x, what do? You take a cube root of everybody, okay? Divided by 4. And then you can get what x is when you plug it in your calculator. You get 2.97 times 10 to the minus 4 molarity. So this is when you want to check the x now. You solve for the x and then check it. You want to make sure it's less than 5%. So you take your x, 2.97 times 10 to the minus 4, divided by your initial that you said was big compared to it. So 0.0250, and then you do 100 because you want to get the percentage, and you get 1.19%. You're like, okay, that was smaller than 5. So I'll just write okay to approximate. So then once you check, you're like, okay, it's good. I was right. I could have just simplified it. So now I'm going to take this x here and plug it back up into my equations to get the concentrations at equilibrium. So H2S equilibrium is 0.0250, right? Remember we said we were, and then it was minus 2x here. So we'll go ahead and put that in here, and it's going to be still, because 2x is pretty small, your answer was 0.0244. So 0.0250 minus 2 times 2.97 times 10 to the minus 4, 0.0244. So see how close it is to 0.25? If there was a 245, you would round it back to the same number. So it's a very, very close number. And then this one here is simply 2x, so 2 times 2.97. 97 times 10 to the minus 4. You get 5.94 times 10 to the minus 4 molarity. And then for S2, it's simply just the equilibrium for X. So it's 2.97 times 10 to the minus 4 molarity. So that's how you would calculate your molarity equilibriums with an example of crossing out the X. HCN plus water and goes to Cn negative aqueous plus H3O positive. Okay, and then it says initially HCN concentration is 0.100 molarity. K of this reaction is 4.9, so it's Kc since it's molarity, times 10 to the minus 10. Find equilibrium concentrations. Okay, so to do this, it literally is the same usual step. So I always say, okay, first of all, let's take a look at the K. Is it small? Yes, it's very small. Is it 10,000 times smaller than this number? Yes, it is. It's a lot more than 10,000 times smaller. Okay, so what we're gonna do is step 1, we'll remember in our head, we're gonna try to do our approximation and then check to make sure it's 5% or less. But in this case here, since they gave us the k, I'm going to go ahead and write out the formula for k. So what's the formula for k? Is these guys on the top to the power of 1 because the coefficient is to the, just 1 there, okay? And then that HCN. Do you put water into? Do you include water? Right, we don't include water because it's a liquid. Anytime there's a solid or liquid, you don't even write it in your equation. You don't put it in your ice table. It doesn't play a part, okay? So we have this here, and we know this at equilibrium. If you put the equilibrium molarities in, it equals to 4.9 times 10 to the power of negative 10, a very small number. Okay, a very small number indicates that this 0.1 here is going to change, but if it's compared to x, the change of x is insignificant to 0.1. So I'm going to go ahead and label out my ice table. So HCN is going to be in there. Water is going to be skipped, so I go to CN. And then I go to H3O. Okay, and then it's ICE. So initially, I have 0.1 of HCN, none of the other things. So I put a 0 there. So what happens now, we have to predict which side it goes to. So to predict that, typically we take the Q and compare Q to K. In this case, our Q is actually 0. It will go towards the side that has the 0, which is the product side. So in this case, this will go up, the products will go up, the 0 side will go up, and the reactant side will go the opposite way, which is going down. So how many x's are we going to be using? This is minus 1x plus 1x plus another 1x. Okay, because they're all coefficient 1. So this is like a really nicely set up where it's like all 1 to 1 to 1, and you can use your math shortcut. It's really nice. Okay, now the good news is this is the type of question you will see in the next chapter. The math will be simple. A lot of times you can simplify it really a lot. The trick to the next chapter is knowing what different types of equations to write, because the next part, they don't even write this for you. You have to write your own equation out. So we'll learn that. But just basically showing this is an example of what you might see, the type of reaction you'll see in the next chapter, okay? So let's go ahead and put the equilibrium terms in terms of x. So this is 0.1 minus x. I just dropped the zeros because I'm running out of space. Right there, okay? And then which one is insignificant? It would be this guy, okay? So these two, you can't cross off because they're compared to 0, and you have to keep them as a number, okay? So k here, I'm gonna rewrite it. That means it's x times x over 0.1, okay? So it's x times x over 0.1, and that equals to 4.9 times 10 to the minus 10. Okay? So once we have this, well, that becomes easy to solve because we cross off that x right there because there was supposed to be a minus x right here. We just crossed that off. So now we know x squared equals to this times that. So that means it's 4.9 times 10 to the minus 11. Okay? Once you get that, to get just x value, you take a square root of everything. So x is the square of 4.9, 10 to the minus 11. Take the square root of that, you will get 7.0 times 10 to the minus 6. And then what we want to do, since we shorten our math a lot, we just want to check to make sure x is less than 5% of 0.1, which is the initial value. So let's take a quick check. 7.0 times 10 to the minus 6 divided by 0.1 times 100. Okay, and then times 100 is to get a percentage there. we get a really small percentage, 7.0 times 10 to the minus 3%. That's so small. That means it's less than 5%, so it's okay to do our shortcut, okay to approximate our math. All right, so now that we're clear that x is good, we take the x and plug it back over here. So we know that HCN equilibrium is 0.1 minus x. So let's plug it in. Oh, 7.0. And such a small number there, you round up to 0.1 again. Okay? And then the other two are just x. So that's easy. We just write down the value for x there. So that would be 7.0 times 10 to the minus 6. 7.0 times 10 to the minus 6. Now, if you're concerned that you might have gotten the wrong values, if you plug these values back into this formula here, you should get an answer that's really close to 4.9 10 to the minus 10. If not the same number, okay? All right, so that is it for the approximation of math parts. We did a few examples and then we showed you without the approximation and then we did some examples with the simplification of math. The last part of our chapter, we want to talk about how it's called Le Chatelier principle, how a system, a reaction that's already at equilibrium, how it will respond if you go mess with it after it reaches equilibrium. Okay, so basically it's like, you know, someone was like, they had a dirty room and then they cleaned it. So now it's like a good state. They're happy it's clean. And then someone else came and dirtied the room up. So what would you feel if you just worked really hard to clean it and then someone came and messed it up? You'd be like, well, I don't like it. I'm going to clean it again. I'm going to try to clean it again because I was trying to get it clean. So it's the same idea here, except you don't like get mad at the other person. The new concentrations, so what will happen is, so if you already reach equilibrium and someone tried to do something to change it, okay? So what the reaction will do is try to fix this problem. So if you increase something, it didn't like it, it will try to decrease what you just put in, okay? So what happens is it will change its concentrations around until it reaches K again. So at first it was K, you disturb it, turn to Q, the system will try to turn itself back to K. The trick is when you turn back to K, the K ratio is the same, but the molarities doesn't have to be the same, okay? So the new concentrations are different, but the K equilibrium constant stays the same. When does the K change? When you change the temperature, okay? So we'll talk about how temperature changes are affected too. So in this case, basically, I'll try to undo the change that you make to it, okay? So here's an example of a reaction. So in this case here, this thing, say N2O4 is going to go to a 2NO2 and it's at equilibrium, okay? So once it's at equilibrium, it's happy, it's got K ratio, it's perfect ratio. Now, what happens is, they said, let's go ahead and add some NO2 in. So they're already at equilibrium, and then you go ahead and throw some extra product in. When you throw some extra product, you're like, you know what, I have way too much product now, that's not cool. So what the reaction will do is try to reduce the product that you just put in and shift itself to N2O4. It will reduce NO2, make more N2O4. That means the reaction shifts to the left. Okay, so whenever you add something, it'll try to fix it by correcting what you just added by decreasing it. So if you add NO2, it'll shift to the left because it's trying to decrease NO2. When you decrease NO2, you get more N2O4. Now, what if we did another scenario? Instead of adding NO2, we're going to add some N2O4 there. Okay, if we added N2O4, what will happen? Well, they're like, well, now I have way too much reactant. Thanks a lot. Geez, now I have to work again. So what is it going to do? It's going to try to reduce N2O4, shift to make NO2. So it will shift to the right, reduce reactant, increase product in that case. So basically when you add something that's already at equilibrium, you add to it, it's going to try to reduce what you just added. Okay, so we'll shift accordingly to which side you added. Now, let's take a look at this picture here. So they're saying here, so this is at equilibrium, and then you add one of the stuff, and then so you add some NO2 there. When you add the NO2, now the blue, all of a sudden you have too much, but then what happens is it's gonna say, okay, well, thanks a lot, now I have too much NO2, let's go ahead and shift to the left, so this is gonna come down, that's gonna go up. And then it reaches equilibrium. But notice at equilibrium, the K ratio is there, but the molarity is up here and there, versus earlier it was down here. So the ratio will be the same, but the numbers of molarities doesn't have to be what it is at original, okay? And then here's another case where they had different scenario where they added N2O4, and they're like, well, I now have too much N2O4, let's get this down. And we gotta mix some of NO2, and then here's another new equilibrium. Okay, so it doesn't mean the molarity stays the same. It just means that the K ratio stays the same. They get reverted back to K, but the molarities are gonna be slightly different. Okay, so that's if you added stuff. Now let's take a look back again on this same picture. What if I remove stuff? Instead of adding, I'm going to remove, okay? So if I had equilibrium here, and then I said, well, I'm going to take out some NO2. Instead of adding, I'm going to take out. So take out some NO2, and the reaction will be like, well, I had a perfect ratio, and you removed some of my stuff. Now I don't have enough of that. So if you remove NO2, they don't have enough NO2. They're like, well, now I just got to shift right. I'm going to take some NO2O4 and make some more NO2 so I get my ratio back. Okay, so if you take away the product, it will shift to the right. Same thing, if you take away the reactant, it will shift to the left because you don't have enough reactant and you should try to make more of it. Are we all following so far? Okay, let me know if you have questions. But that's if you take away stuff and you add stuff to a reaction with the right equilibrium. Now let's take a look at another scenario. What if you were changing the volume and the pressure? So here's the thing. For volume and pressure, they're kind of opposites, okay? Basically, you see this picture here? It says increased pressure, that means it squeezes it down. When you squeeze it down, you increase the pressure because you put more weight on it. Increases the pressure. You see how the volume here is smaller compared to this one? So pressure, when pressure is high, volume will be low. When pressure is low, volume will be high. They're opposites, okay? So when you have this scenario, volume or pressure, it really just, sometimes they'll say, okay, what happens if I decrease the volume? What happens if I increase the volume? Or they can say, if they really want to say decrease volume, they can just say increase pressure. It means the same thing. Or decrease pressure, it means increase the volume. Okay, so you gotta remember these changes here. Now, so in this case, over here, what we're going to take a look at is, so if you squish it down and there's not a lot of space left, we want to start counting moles of gas in our reaction. So over here, the reaction is N2 plus 3H2 goes to 2NH3. So on the reactant side, there's 4 moles of gas, and on the product side, there's 2 moles of gas. So if you were to count space of how much the gas space is, typically the 4 moles of gas, you know, would want more space than the 2 moles of gas. So they're saying, well, if you squish it down, there's not going to be as much space for them to play around. Because if you keep squishing it, they turn to liquid and they want to stay gas. So that means they want to try to shift to the side with less moles of gas. So if you increase the pressure or decrease the volume, the reaction will shift to the side with less moles of gas because there's not enough space. Okay, so in this case, the less moles of gas is to the right, so they'll shift to the right. Now, if you did the opposite, if you open it up, let it get more volume by decreasing the pressure, putting a smaller weight on it, that means it has more space. They're like, oh, let's go out and play. We have more space now. So they will shift towards the side that has more moles of gas. Okay, so basically we have to start remembering, okay, so if I, do changes in volume, it's basically, if I say decrease volume, it means the same as increasing pressure. When I have a small space here, small volume, it will go to the side with less moles of gas. When you have a lot of space, high volume, by decreasing the pressure, you will go to the side that has more moles of gas. Okay? So let's keep going. What happens if you add a catalyst? Does it change your equilibrium? You gotta remember, catalyst has nothing to do with equilibrium. Catalyst just makes things go faster or slower, but it doesn't change the position of K. Okay, so if you do catalyst, say it will be no change. Same idea here if you added something inert. So in this case here, say in this picture here earlier, if we were to add NO2, make a change. If we add N2O4, make a change. But if you add an inert gas like helium or argon, then like basically group 8 stuff, okay? It will not change a thing, okay? Because it doesn't affect the concentrations of those gases. So I'm gonna go ahead and write a question out for you guys here, and let's try to see if we can practice what we just learned. So the equation is 2KClO3 solid goes to 2KCl solid plus 3O2 gas. Okay. How would you write the K for this problem, this reaction? Do you write the solids? No, we don't write the solids, right? We don't write it at all. So I'll write OK as, well, it's just basically O2 to the power 3. You guys remember the Kc and Kp thing? We have to count the number of moles. Remember? What was my delta N here? Delta N for this question would be what? My moles of products minus moles of reactant. And it will be 3 minus nothing, 0, because these are solids, so you don't count them. So it will be 3 minus 0, it will be 3. Okay, so that was just a quick little review from previous sections. Now, let's take a look at this picture here. Now, so let's say if this reaction has gone to equilibrium, and what you did was you decreased the volume. Now, when you decrease the volume, what does it mean in this pressure terms? I could also say, what? Increase pressure. Okay, which way will it shift if I decrease the volume? So when you do volume changes, you look at the side with a more or less moles of gas, right? Less volume, shift to the side with less moles of gas. So this is 3 moles and this is 0. So if you decrease the volume, it would shift to the side with less gas, which in this case is going to be to the left. Okay? Now, let's take a look at another scenario. What if we did the opposite? If we increase the volume? If we increase the volume, we're decreasing the pressure. So it will shift to the side that has more moles of gas, in this case, to the right, because this is 3 moles of gas, 0 moles of gas over here. So this will shift to the side with more moles of gas, which is to the right side. Okay, now remember, if we add an inert gas, what happens? Nothing happens, okay? We'll say inert gas is no effect. What else is no effect? When you add a catalyst, okay? All right, Let's see. So that's if you did volume, adding stuff, and let's say if I add another one, let's do another one, okay? If I added oxygen gas, which way would it shift? You add this guy, which way would it shift? It would shift to the side to reduce the oxygen, make more of the other stuff, but in this case it's all solid. So it would shift to the left. If you removed oxygen, it would make it shift to the right to make more oxygen, okay? Can you write number of moles each side? So this here is 3 moles of gas. This here is 0 moles of gas. Okay? All right. So now let's take a look at what happens if you change temperature. Okay? We're going to talk about how we change temperature. Now remember, when we said we change temperature, what was the important thing that changes? The K value itself also changes. All these guys here, the shift right and shift left, things like volume, pressure, and adding and removing the products or reactants, it doesn't change the K. The K value stays the same. Now, as soon as we start changing temperature, okay, then our K will start to change. How does this connect with concentration gradient? Well, if you add or remove things, it changes your concentration, and the pressure-wise, it changes typically the concentration of your gases, which we really are looking at partial pressures of gas. I'm not sure what you mean by gradient, because it's trying to, you know how when you don't have equilibrium, it's Q, and Q is a different ratio from K. So Q is trying to work itself back to K every time, basically. There's no like high to low. It's just if you take away, it goes to low and it's trying to go back up. So it just depends on what the change is. Like what disturbance you put in, okay? So just remember, this is the whole concept of Q trying to turn itself to K. Now, let's take a look at if we change our not concentration, we were talking concentration here. Now we want to talk about temperature. To do temperatures, we have to do a quick little review about exo and endothermic again. Okay, so let's just do the first one. We'll talk about exothermic reactions first. So what in the world is exothermic again? Exothermic reactions, their delta H sign was what sign? It was negative sign. So something you have to remember from Chem 1. But if you don't, we have a little review right now. And if we were to draw the little graph out, the reactant has a higher energy than the products, and it goes down that way. So when it goes down in energy, this difference here is your delta H. Okay, and because it's going down, it shows a negative sign. Basically, you're releasing some sort of energy. Usually it's in the form of heat. Okay, so you're releasing something, it's coming out, energy is leaving your system, and delta H is negative. So in this case, if you're releasing energy or heat, this sort of counts kind of like a product. Okay, so if I were to write a reaction that looks like this, and when I say, well, this is AA, not AB. Well, let me change that. A of A plus B. Just assume none of these are solids or liquids, okay? If this was an exothermic reaction, I would have heat on my product side because it was released out as a product. Okay, so we're releasing heat as a product. So now, let's say if I have something that's an exothermic reaction, so I have to remember where I'm going to place my heat, and then we say, okay, now I'm going to increase my temperature. Now, when I increase temperature, what am I increasing? I'm increasing heat on the product side. You see that? So basically, I'm also increasing heat. In this case, it's a product. So now I got too much product. So a reaction will shift left. Okay, when it shifts left, what happens to your K? So because we are messing with the temperature, we have to see, so we say, oh yeah, it's gonna shift to the left. We know that part from earlier. But let's take a look at what the K will be. So in this case, C to the power C, D to the power D, A to the power of A, B to the power B. So we're saying reaction will shift left. That means we're gonna reduce this and make more of this. But because the temperature changed, this is going up. Oh no, that's going down. This for reducing the products. This is going down and this one's going up. So this number, the top number is becoming smaller. The bottom number is becoming bigger. It's gonna shift to the point where the K will change. You know how earlier we say if you don't change the temperature, it will just shift up and down, but it will go back to K. If you increase the temperature or change the temperature, it actually doesn't go back to the original K. The K will change. So in this case, your K will be smaller because the top number will be small, the bottom number will get bigger. So K becomes smaller because products are going down and reactants are going up. Okay, so that means if I had an exothermic reaction and I increase the temperature, the K actually will become smaller because the reaction is shifting left. Okay, so now let's take a look at the opposite scenario where if you decrease the temperature on an exothermic reaction, it would do the opposite, agree? So if you're decreasing temperature, you're removing or reducing, I guess. Well, I wrote remove, we'll commit to that. Removing heat on product side. So we don't have enough product, not enough product stuff. So reaction will shift to the right side, towards the product side, okay? So because it shifts towards the product side, you'll see that your C to the power C, D to the power D is going up, and your A and B are going down. So in this case, K becomes bigger. Because products are going up and reactants are going down, okay? So you have to remember, okay, what does exothermic mean? Exothermic means releasing heat, so heat is on the product side, and these are how the K will change and which way it will shift, depending if I increase or decrease the temperature for an exothermic reaction. So then sometimes they don't tell you upfront it's exothermic. They just say, they'll write an equation, and they'll write a delta H next to it, and they'll say delta H is negative, blah, blah, blah. So because it says negative, then you'll know it's exothermic, then you put your heat on the product side. So that's why you have to remember exo versus endo, okay? Now let's take a look at the endothermic reactions this time. So basically endothermic will be the opposite picture here. So I'm gonna shift and write about endothermic stuff. So endothermic is the opposite, where delta H is a positive change, where your reactant is lower energy than your product. So your reactant was down here, product will be up here. And it's going to go up. And the distance between that to delta H is going to be positive value. So it doesn't release heat, it receives it, or heat is a reactant in this case. You have to add in energy. Okay, so energy is a reactant, or heat is a reactant in this case. So we said if you had a reaction of A, B, and it goes to C, and D. And we say, okay, well, this one is endothermic. Sometimes they say it's endothermic, sometimes they say delta H is positive. Sometimes it says when you touch the flask, it feels hot. And feels cold. I'll write it down here. Cold to touch. Remember, endothermic is cold to touch. The flask is cold to touch. Exo are added up here. So flask feels hot. Warmer. Because it's releasing heat, you feel the heat. Okay? So this one, the flask will be cooler because it's absorbing the heat away. So when you touch it, it's like, oh, it got colder. So that means heat is my reactant. Okay? So once we have that, if you increase the temperature, we are actually increasing reactants because heat is there on the reactant side. Okay? So when you increase reactant, you're like, oh, I have too much reactant. So too much reactant. So which way does it shift? It will shift to the right. Reaction shifts right. Okay? So you see how it's kind of like opposite of what we were just looking at. So I'm trying to write it all out. So when you study, you'll have all the stuff laid out in front of you. And I'll show you some example questions. So basically say, okay, this is endo, this is exo, we increase or decrease the temp, what happens? There's a shift right, shift left, what happens to the K? All right? So in this case here, if you're shifting to the right, your K, CD is going up, AB is going down. So this stuff is going up. And then the A and B is going down. So K becomes bigger. Okay? And then if we did the opposite by decreasing the temperature, we are removing heat. So that means we're removing a reactant. So we have not enough reactant. So the reaction will shift to make more reactants, which is to the left. Now when it shifts left, you're making more A and B, less C and D, so K will be smaller. So I'll write it out. Less C and D, more A and B. K will be smaller. Now remember, K only changes if you have a temperature change, okay? So let's try it out, okay, with an example. And then we'll do a bigger example where it talks about all the different stuff. I wanted to write out one example first, and then we'll show you an example from the slides, okay? All right, let's go ahead and change to the next page. So here's my reaction. It's a CaCO3 solid goes to CaOS plus CO2 gas. And they say this is endothermic. Now, what are the signs? Oh, you can't see. Never mind. What are the signs of endothermic? Endothermic means delta H is positive, remember? Another way they can hint around it, it says the flask is cold to the touch. So these are the things that they'll tell you to tell you it's endothermic. Okay. Now, what's the change? So what's the effect of increasing temperature here? Okay. What's the effect of increasing temperature? For this reaction, if they tell you it's endothermic, if they tell you delta H is positive, or if it's cold to the touch, the flask becomes cold to the touch during reaction, okay? So if these signs here tell you that you need heat as a reactant, so you have to write your heat over here. So you add this in, okay? And then say, well, if you're increasing temperature, you're increasing this guy. So you got too much reactant, it will shift to the right, agree? So now when we say shifting to the right, I can't spell. There we go. We're increasing CO2, decreasing the stuff here. So our K is actually going to go up, okay? Now, if you were to do the opposite by decreasing the temperature, what would happen? It would do the opposite change, okay? It would shift to the left, and then your K would go down. So you just you'll see a lot of these problems here on your quizzes, on your homework as well, dynamic study modules. But just keep practicing and you'll see them on the practice exam too. But they'll just ask you which side will it shift. You just need to know like a combination. So this is how, if you increase temperature, decrease temperature, where it will shift. And when you change the temperature, remember the K changes as well. Now, and then the other stuff is they'll ask you, what if I add products, add reactants, or remove product and remove reactants? So here's another example for you guys, okay? This is from slide number 69. This is basically the end of our chapter for chapter 16 here. So let's take a look here, okay? So it says 2SO2 gas plus O2 gas goes to 2SO3. And it says with delta H as negative 198 kilojoules at equilibrium. So because it's negative here, means it's exothermic. And this question we just had was endothermic, right? So the heat was on the reactant side. This one is negative, so the heat goes on the product side. So I wrote a little heat here. But just remember the heat is on the product side for this question, okay? It says, how will each of the following changes affect the equilibrium concentrations? So we'll just have to say to shift left, okay? So if you add more oxygen to the container, you add more of this guy, which way will it shift? Shift to the, does it go to the right? Or does it go to the left if you add more oxygen? Right, correct. It would shift to the right because if you add more oxygen, you have a lot of the oxygen here, and it's going, well, I have too much oxygen now. Let's reduce it and make more of my product and reduce the oxygen. So it would shift to the right. Now the next question is condensing and removing SO3. So you're removing this guy, removing a product. Now you won't have enough product. So which way will it shift again? This time, if you remove the product, you don't have enough of this. So since this is on the right side, it would shift to the right again. Very good. Okay, so you just have to kind of like, so these questions are basically like, this is one question, here's another one. So when you see the question, it will just be, okay, blah, blah, blah. What happens if you do this? So I'm just combining a lot of these things together, okay? So we say, okay, that one, the second one also shifts towards the right, that's good. Now the next part, it says, what happens if you compress the gas? So compress the gas means you squish it together closer. That means there's less space, so less volume, okay? When you have less volume, remember we shift to the side with less moles of gas. So let's count the moles of gas here. This side here is 3 moles of gas. This side is 2 moles of gas. So if you're squishing them close together, it's going to shift to the side with 2 moles of gas, correct? So in this case, it will also shift to the right. Okay, so make sure you stop me or ask questions if you're not following, all right? So this one, the third one, is also shifting to the right. Let's take a look at the next one. It says, what happens if you cool the container? So cooling the container means reducing the temperature, okay? What happens if you reduce the temperature on this reaction that is exothermic, that the heat is on the product side? If you cool it, you're removing heat. Right, so that means it will shift to the right. Very good. If you're asking about shifting to the right or left, shifting towards the side of SO3 is to the right. Shifting to the side of SO2 is shifting to the left. Okay, so in this case here, if you cool the container, you're you're removing heat, so you don't have enough product side. It will shift to the right again towards the side with SO3. All right, let's take a look at the next scenario. Very good, guys. Everyone's following. If we double the volume of the container, so this doubling the volume is the opposite of the compressing the gases, agree? Because now we're like unsquishing them, giving them a lot of space to run around. So that means it will go to the side with more moles of gas. So which side is that? It's to the left. Very good, because this side has 3 moles of gas. So it's a matter of remembering, okay, if we're talking volume pressure, look at moles of gas. If you're adding reactant or product, we just go to the side to compensate for the change. Now the next one here, this is warming the mixture. That means we are going to heat things up. So if you're heating things up, you're increasing heat, which is on the product side. Which way is it going to shift this time if you warm the mixture? Very good, it's going to shift to the left. Because if you increase the heat, you got too much heat on the product side, then it's gonna be like, well, I gotta reduce some of the heat here and try to like, shift to the left, okay? Then it says adding inert gas helium to the container. What do you do? Inert gas is a trick question. No change, okay? So remember that. What about catalyst? Does catalyst make it shift to the right or left? Right, catalyst is also no change, very good. All right, so that is actually the end of chapter 16.